is 5 degrees above this boundary temperature. Quotient temperature is 5 degrees below this boundary temperature. How do we find out all this boundary temperature? How many horizontal lines do we need? Cold stream, you add 5 degrees, 65, 185, 35, 135. Hot stream, you minus 5 degrees to get intermediate temperature, 180, 175, 40, 35, 150, 145, 40, 35. The next thing you do, you arrange this for boundary temperature. For highest 185, 175, 145, 135, 65, 35. Arrange in decreasing order. How many of this temperature? 6. So, in the future, you need to draw 6 horizontal lines. You put those temperature right there. Why do I need this temperature? You can use a single boundary temperature, intermediate temperature, to represent both hot and cold. Hot stream, 5 degrees above. Cold stream, 5 degrees below, which is 1/2 of your delta T mean. And how do we set up this table? To this table, we're going to use another example to repeat this exercise. So you go to page 18. We do this through another example. Look at page 18. 2 cold stream, 2 hot stream. Temperature, capacity flow rate, and dot mass flow rate times heat capacity. It has unit of kilowatt per degree C. So now, go to page 19, we're going to do this exercise so you can refresh your memory. How do we do this? Are you ready? Cold stream temperature, 60 to 180, 30 to 130. Hot stream temperature, 180 to 40, 150 to 40. And boundary temperature, hot and cold, 5 degrees, 5 degrees. Delta T mean, 10 degrees C. In other problem, you may have delta T mean of 20 degree F, then this is 10 degree F, 10 degree F, 1/2 of delta T mean. Okay? Now, to find this boundary temperature, one single temperature, to represent both hot and cold. So you add 5 degrees to cold stream, 65, 185, 35, 135. You minus 5 degrees to hot, 175, 35, 145, 35. And then you arrange this in decreasing order. Wait a minute. Yeah, here's 185. Okay, 175. Yeah, 145. 135, 65, 35. Correct. So we combine the two, arrange them in decreasing order. So when you set up this table, you need 6 horizontal lines. 185, 175, 145, 135, 65, 35. In terms of real stream temperature, hot and cold, hot stream 5 degrees above, so 190. Cold stream 180. The difference is delta T min. 180, 170, 150, 140, 140, 130, 70, 60, 40, 30. These are the real stream temperature. Those are intermediate temperature. So now, instead of this table, hot stream 180 to 40, 180 to 40, cool it down. Hot stream 2, 150, 150 to 40. Cold stream 1, 60 to 180, 60 to 180. Cold stream 2, 30 to 130. Now, we need to put down capacity flow rate next to the stream. 2, 4, 3, 2.6. 2 kilowatt, 4 kilowatt per degree C, and 3 kilowatt per degree C, 2.6 kilowatt per degree C. We need this to find out required energy. All right, any question? This is how you set up the problem. Now, the way we do it, we combine both hot stream. We call it composite hot stream at each temperature interval, what are the available heat? No hot stream here, 0 kilowatt. Hot stream 1, 180 to 150, 30-degree temperature drop. For each degree of temperature drop, giving out 2 kilowatt heat. So 2 times 30, 60. Right there's the middle of these two lines. Now, here you see 2 streams. 10-degree drop times 2 plus 4. 60. Here, 70-degree temperature drop times 2 plus 4, 420. 30-degree temperature drop times 6, 180. What do this number mean? When you cool down hot stream in this temperature range, it gives out 60 kilowatt available heat, available from hot stream. When you reduce its temperature, cascade heat, you put down this time a number right above the boundary line, inside parentheses, 0 plus 0, 0 plus 6. Cumulative number 120, 540, 720. So that's what you're doing. Total amount of heat released by both hot stream, 720 kilowatt. No question? Now, we're going to consider both cold stream together. We call it composite cold stream. Require heat. To heat up cold stream 1 by 10 degrees, 3 kilowatt per degree C, you need 30 kilowatt. Here, 30 degrees times 3, 90 kilowatt. 10 degrees times 3, 30 kilowatt. Now here's trouble. Both cold stream require heating. Raise the temperature by 70 degrees times 3 plus 2.6, 5.6, 392. Lastly, 30 degrees times 2.6, 78. This column means to raise either cold stream 1 or 2 or both together in each temperature interval, how much heat you need to add to the cold stream. Cascade heat, 30, 120, 150, 542, 620. Are you okay? Now, composite, grand composite stream. That is all the hot stream, all the cold stream. You look at here, if you call this column A, column B, net heat C equal A minus B. What does that mean? In this temperature interval, hot stream cannot provide any energy. Cold stream requires 30. The difference between the two, minus 30, that is heat deficit. In order to heat it up cold stream 1 to 180 degrees, that heat must come from outside through utility. Hot stream cannot help you. So 60, 90 minus 30. 60, 30 plus 30. What does that mean? Heat surplus, positive. 420, 392, surplus, 180, 78, 102, surplus. You notice here, heat deficit is surplus. This is a simple problem. Above the temperature, heat deficit. Below temperature, heat surplus. You do not have change of sign. Much easier. Later on, you will work on problem. You might have plus, minus, plus. What is the true amount of heat deficit and heat surplus? You need to look at this cascade heat. So, 0, here, no, not 0, minus 30, okay? Minus 30, minus 30, minus 60. Minus 60 plus 30, minus 30. Minus 30 plus 28, minus 2. Minus 2 plus 102, plus 100. So, this is a cascade heat, similar to what we do here. Now, let's look at it. 0, you look at here, A prime, B prime, C prime equal A prime minus B prime. 0 minus 30, minus 30. 60, 120, minus 60. 120, 150, minus 30. 540 minus 542, minus 2. 720, 620, 100. You see the relationship? Oh, don't do that. What did I do? What happened with your touch? Oh, right. Nope. Eh? What happened? What did I do? I touched something. Somebody come forward, see what happened. What happened? What happened? Does it come? No, I don't see it. I don't see it. That's not. No, this one. Ah. No. I don't know. Who's coming help? Lighting, right? Come this way. I never touched it.
Oh, here comes another.
No. I don't see it. Oh, you reversed it.
It was already reversed.
Good. No, reversed it. The nice song is reversed. Rotate angle, okay, just keep turning. I don't know. No, reverse.
I don't want that. So maybe it is go back to the They're just it's a very big transfer. Like they're all actually really
Yeah, I played for one semester. Just come back.
Yeah, why aren't you?
Also do on Saturday.
Still reversed. What's going on? Okay, let's continue. Get this done. Okay, we got time. So now, want you to pay attention here. What is the minimum heating utility requirement? You only look at the cascade heat, the largest negative number. That is the total heat deficit. Okay? The largest negative number. How do you cover this quotient heating with heat deficit 30, total 60? You move this number to the top, change the sign. External heating utility. QH mean is 60 kilowatt. You add 60 kilowatt from high temperature heating utility, steam. With that, you do it like this. So, if I draw a line, 185, 175, 145, 135, 65, 35. Dash intermediate temperature. If I provide QH mean 60 kilowatt from the top, between 185, 175, is 30 kilowatt heat deficit. 30 kilowatt heat deficit. 30 kilowatt surplus. 28 kilowatt surplus. 102 kilowatt surplus.
Professor, can you move it down, please?
Mm-hmm.
Thank you.
Make it smaller. Okay. Now, you add 60 minus 30, you have 30 remaining. 30 minus 30, no more surplus. 0, 30, 30. 30, 28, 58. 58, 102, 160. That is heat surplus. How do you represent this in a table? 60, you draw a line there. 30. 30 minus 30, 0. 0 plus 30, 30. 30, 28. 58. 58, 102. 160. That is exactly what I got here. Okay? So, QH mean minimum heating utility requirement is largest negative number. You need to cover the heat deficit by positive heat utility. 160 kilowatt. In order to cool down hot stream to the target temperature with heat surplus, you need cooling water. So this is QC mean, cooling water, 160 kilowatt. And this 0 is the pinch point. What do we mean by pinch point? You look at this horizontal line, hot stream, 150 hot, 140 cold. What's special about pinch point? I said it before, let me repeat it. Above the pinch, process is cold. Cold means heat deficit. Need steam, heating utility.
Do you mind refocusing the screen? Thank you.
Okay. Below the pinch, process is hot, heat surplus. Need cooling water. You understand the meaning of pinch point? Now, pinch point exists only when you need both heating and cooling utility. Yeah?
Under what circumstances would we need additional cooling rather than additional heating from steam?
Okay, hold it. Let me finish the statement. If you only require external heating, no cooling, there's no pinch point. Likewise, if you only require external heat, cooling, no heating, there's no pinch point. Okay? Pinch point exists only when you need both. To answer your question, you just look at this table, okay? And you can even move this table, just line down here. Everything here is heat deficit. Then you only need heating utility, okay? So this, you move this line down here. Move this line down here. All this is a negative number. That means you only need external steam, right? If you move this line above, you find out everything here is positive, then you only need cooling utility. Do you get it? Any other question? Yeah.
Can you explain again how you got the numbers for the shifted cascade?
Which number?
For the shifted cascade.
Oh, I add 60 here, right? And take care of this heating, consumes 30. So, what's remaining? 30, right? This came from external steam. And this, to heat up this hot cold stream, you consume 30. 30. Now, heat goes from top downward, just like this arrow. I have 30 kilowatt energy, and this temperature interval, 140 to 170, short of 30 kilowatt, provide that, there's no more remaining, 0. 0, 30, he's surplus, 30. 30 plus 28, 58. 58 plus 102, 160, just like here. 60 minus 30. 30 remaining, like this. 30, consume 30, 0, that's this. 0, 30, 30, 30, 28, this all his surplus. Are you okay? Any other question? Oh, I don't have enough time. I don't like it. Okay. Now go to page 10. Go to page 10. Let's explain some plot, okay? I may not have time for all the plot, but I can get started. Okay, let's look at this column, boundary temperature, and last column, okay? This is Grand Composite Stream. Where is the Grand Composite Curve? Plotting this column versus this column. You see that on page 12. I've explained this. That will be the end of today, page 12. This intermediate temperature, that is hot minus 5 degrees. Cold plus 5 degrees. Okay? So, I have 185, 175, 145, okay? So, 185, 60. This temperature, 185, 600. That is 185, 600. 175, 300. 175, 300. 300. This is kilowatt. And 145, 0. This is our pinch point. 145, 0. 135, 300. Here, 60, 860. 35, 200. And you notice this is a pinch point. This has a famous name, Grand Composite Curve, or GCC. Now, where is minimum heating utility requirement? Above the pinch, process is cold, right? Above the pinch, process is cold, heat deficit. And how much heating do you need? This distance is minimum heating utility requirements, 600. below the pinch, process hot. Now, you want to cool down those. You want to cool down those hot stream, okay? Because surplus this distance is minimal cooling utility requirement. You see here? This is the grand composite curve. Any question? And this is the most important curve in heat integration. I will demonstrate to you through different examples in the future. You go to commercial software for heat integration, they will draw the grand composite curve, okay? And our table is such that we can duplicate all the important curve in heat integration through this table one by one. Now, I will explain page 11, hot and cold composite curve on Wednesday. It take more time. I'm going to stop right here.